Hi, my name is Michael de Podesta, and this is a video of a talk I'm going to give tomorrow for Physics in Action in London. And the title of the talk is this: Is it possible to live a carbon zero life? Now, this is an important question in general, but it's a particularly important question for me because I've been trying to do it for the last couple of years. I've spent my life savings trying to reduce my carbon emissions, and I'm trying to change my lifestyle. And so this talk is about whether it's really possible. And at the end, I'll tell you the answer. So why does it matter? Why would I even try to do such a thing? Well, there are two phenomenal epoch-changing events going on Earth at the moment. The first you probably know about is climate change. The CO2 we put in the atmosphere is changing the climate of the Earth. And I'll be talking about that a bit in the first part of the talk. But there's another thing going on which you may not have gathered was a thing, which is an energy transformation. That since the dawn of time, the way human beings have manipulated the world is we've used the energy from things other than our bodies. So we've used animals to do work for us. We've used, but the thing that's defined humanity is our ability to use fire. We burn stuff, and this has allowed us to live in colder places than we would normally. And it's also defined how we've lived in the landscape, because we've gone to places and then burnt the wood. We've built things with it and then burnt the wood. And then when we ran out of wood, we started burning rocks. And then when we ran out of rocks to burn, we started burning oil and coal. And we went to great lengths to get all these commodities. But now, while in my lifetime and throughout the whole of your lifetime, there's a new possibility. We can get energy without getting stuff hot, without burning stuff. And that's renewable energy. And renewable energy is now the cheapest form of energy there has ever been in human history. And so this is going to change things. It's not clear how it's going to change things, but it's going to change things. So I want to talk on both these topics. And the first one is, why does the concentration of CO2 in the atmosphere matter so much? You may know, I think many people have not fully appreciated the reason why that matters so much. And then the second one is, how do we stop emitting CO2? What are these new technologies that we can use? But yeah, how do we stop burning stuff? So why does the concentration of CO2 in the atmosphere matter so much? Well, it's to do with energy balance. So here we are, we live on Earth. It's a great place. And one of the best things about it is it's bathed in sunshine. 24/7 sunshine pours onto the Earth and warms the Earth up. But if it were just sunshine pouring onto the Earth would keep getting hotter and hotter and hotter, which is not what happens. The Earth's temperature is roughly stable. So we've got to get rid of this energy which comes in, and the way we do that is by radiating infrared light out into space. And so when the rate at which energy comes in from the sun is balanced by the rate at which energy goes out into space, then the Earth's temperature is going to stay constant. It's just like pouring water into a bucket with a hole. When the rate at which you're pouring water in is equal to the rate at which water leaks out through holes, then the level will stay stable. So let's take a look at this. So this rectangle here represents all the heat input from the sun in 1 year. And it's an absolutely massive amount. Let's not worry about the numbers. But when the temperature is roughly, that makes the Earth warm. But when it's balanced by infrared radiation, then the Earth's temperature will stay stable. So I've drawn this one in red because it's infrared. Now, on the same scale, I want to draw all of human energy production. So you can see it's just here, and I've drawn it a bit big just so you could spot it. So I'm going to reduce it to the true scale value. It's about 1/10,000th part of all the energy that arrives on Earth from the sun, that's all humans use in our nuclear power, burning oil, coal and gas and so on. Quite astonishing. The reason that's important is that it's not the use of energy per se which is the problem, it's affecting this balance. We'll see more of that. So we've got the sunshine coming in and the infrared light going out. So let's just imagine if the Earth had no atmosphere, then the sunlight on average would come in and its average value would be about 240 watts per square metre. That's averaged over the whole of the surface of the Earth, night and day, and all the latitudes and so on. It's about 240 watts per square metre, and that would warm the Earth. The Earth would warm up and radiate, and in equilibrium it would radiate 240 watts per square metre back out into space. This would just be vacuum here. And we can work out what temperature of the Earth that would correspond to, and the answer is 255 Kelvin or minus 18 degrees Celsius, which is very cold. It's much colder than the actual average temperature of the Earth. And so the reason that we're warm at that is because of the atmosphere. So let's take a look at what's in the atmosphere that provides this warmth onto the surface of the Earth. So if we picked 100 molecules at random, in general we get about 80 nitrogen molecules, about 19 oxygen molecules and 1 argon molecule. If we picked about 1200 molecules, we'd see a few water vapor molecules here, water. And if we picked about 10,000 molecules, we could now begin to see the carbon dioxide molecules. Now, in case you're not very sharp-sighted, let me show you where they are. There they are. There are about 4 of them, typically in about 10,000 molecules. So the way we talk about the concentration of carbon dioxide is in terms of how many carbon dioxide molecules there are relative to air molecules as a whole. And the first thing is you can see it's a trace gas in the atmosphere. It's quite astonishing that it matters at all. So in this concentration, there are 4 CO2 molecules in 10,000 air molecules. So there'd be 40 in 100,000 or 400 in a million. And so that concentration is called 400 parts per million or 400 ppm. Now, let's just think about how we might expect to see the effect of that when we look up at the sky. So when we look up at the sky, we see blue and we see clouds in general, some combination of these. So the clouds we know are water vapor droplets. So the water is liquid water, and that's transparent to visible light, and so all we're seeing is the scattering of light. It's coming in one direction and it reflects off little droplets and goes in a different direction, or is transmitted and refracted out in a different direction. And so all the outside of the cloud just appears white. It's just redirecting the sunlight that arrives on the top of the cloud. And we also see blue sky. Blue sky is really, really interesting. If the atmosphere were completely transparent, we would just look out and see the darkness of space every day. We'd see the sun in the sun direction, but the darkness of space everywhere else. But in fact, air isn't transparent. What happens is that as sunlight goes through it, so here's a light wave, the electrons on the atoms of oxygen and nitrogen that make up the bulk of the atmosphere, they start to shake and they re-radiate some of that light in all directions. This is called Rayleigh scattering. And so what happens is if you look up through the atmosphere out against what would be the darkness of space, you're looking at a column of air that's perhaps 10 kilometers thick, and it's glowing slightly. Now, it glows more for blue light than red light for complicated reasons. And so when we look up, we see blue, and that's the combined radiation from all the air molecules in the column above us. Now, what's very interesting, so that's how light comes through the atmosphere. It basically comes through uninhibited, but it's got a few things that happen. But if we could see in the infrared, we would see something completely different. If we could see in the infrared, every day would be foggy. We would see nothing every day. We wouldn't see the blackness of the sky at night. We wouldn't see we see a sort of glow when the sun was open, but when the sun was had risen, but it would just be foggy every day. So this infrared fog is caused by water and carbon dioxide molecules. It's not caused by 99% of the gas in the atmosphere. It's caused by these trace gases in the atmosphere. And the density of the fog depends on the concentration of water, vapor and carbon dioxide. What these molecules do is we've now got infrared light. It's got a longer wavelength than the visible light. And instead of shaking just the electrons on atoms, it's actually causes vibrations of the molecules, the way the distance between the oxygen and the hydrogens varies. And because there are electric charges there and they're jiggling up and down, they re-radiate some of the light, and some of the light comes back. It's the same for carbon dioxide, and so here's a carbon dioxide molecule, and it's caused to absorb some of this radiation and re-radiate it. And so infrared light going this way through the atmosphere finds that some of it is scattered back. So if we revisit our previous diagram, so this is where we were on the last diagram, but now we've got an atmosphere, and some of this radiation that was going out comes back. And when you add it up, it's quite a lot. It's about 150 watts per square metre. Not quite as much as the sunlight that comes in, but very, very substantial. One of the early scientists, Guy Callender, called this sky radiation. That warms up the Earth, and the Earth's temperature becomes about 288 Kelvin, 15 Celsius or so. And that's the situation that we experienced about 100 years ago. So you might be curious to see that such a small concentration of carbon dioxide could have an effect. So I did this little experiment, which was I put some 400 ppm of blue food colouring in water. So that's 0.4 of a gram in a litre of water. And I filled up one of these, a measuring cylinder with it. And so you can see the sort of colour of the measuring cylinder. So here's a video. Let's just look. You see the colour, you can see through it. But if you look at the top now, can you see how much darker it is when you look through a long depth of it? So this is comparing the two. This is the view from the top, and this is the view from the side. You see that when you look through a long column, even at a very low concentration, you get a lot of absorption. And that's the same in the atmosphere. So we're looking through kilometres of the atmosphere, and it makes the atmosphere opaque. So 400 ppm of CO2 in air, even small concentrations of gases can affect transmission through the entire thickness of the atmosphere. Let's talk about now the CO2 that we're adding to the atmosphere, anthropogenic CO2. So we're putting in around about 36 billion tonnes a year of carbon dioxide. It's an unimaginable amount, and you can see since 1700 it's basically nothing, and then as the Industrial Revolution kicks off, it gets bigger and bigger, but it's not really till after the Second World War that this rate just shoots up, 36 billion tonnes a year. And what's that done to the concentration of carbon dioxide in the atmosphere? Well, historically it was about 280 ppm. This year range is covering up to this year, from 1700, and now there's currently about 420 parts per million in the atmosphere, and it's going up by about 2.5 parts per million per year. So that is a 50% increase. So if we imagined the fogginess at the start, so that's one level of fogginess, what we've done is, as far as the infrared light leaving the Earth is concerned, we've increased the density of the fogginess of the atmosphere. So what's that done? What's that extra CO2 done? Well, in this diagram, we've added 50% extra CO2, and that's made a difference here of around about 2 watts per square metre. And the temperature here is changing by, I put 2 degrees, but we don't know exactly where it'll end up. So what we've done is, on this energy balance diagram, what we're doing is we're affecting the rate at which infrared light can leave the Earth. So typically it's about 1% here, and that's caused this imbalance. and that's what's causing the entire Earth to warm up. So there we've got heat input from the sun, the energy imbalance. Here's the total of world energy production, large and then drawn to scale. And so the key thing is that it's not this energy that's in itself that's a problem. It's this energy imbalance, which is vastly more than humans are able, vastly more energy than humans can produce. So let's just see what's happening. Well, here's the global temperature anomaly. That's the difference in temperature from the 1850 to 1900 range. So we plot that along here, and you see that currently we're up at about 1.2 degrees or so. On this graph, each blue dot is an estimate of the surface temperature of the Earth made from meteorological records. And the grey bars are the uncertainty in that, and the red line is the 10-year running average. And you can see what's happening here is that this is going on like this, and we expect it to pretty much go on exactly like that. This is my life. In my life, I wasn't really aware of climate change till around about 20 years ago. But even then, I wasn't really aware of it in my daily life. I knew about it intellectually. In the last 10 years, it's become completely obvious to me that the climate has changed. It's just not, living here is just not like what it used to be. It's not the climate I grew up in. And the reason I'm concerned about that, well, I'm planning to die in 2040, so it's not really my problem, but I'm worried about people born in about 2005. I'm worried about my own children. This matters to me more than anything else I can think of. I am terrified that very, very soon this will be at 1.5 degrees and 2 degrees, and I am committed to trying to do everything I can to stop that curve going up. So here's the summary of part one. Why does CO2 emissions matter? Infrared transmission through the atmosphere is strongly affected by the CO2 concentration. The fact is the climate that your parents grew up in is gone. It's gone forever, completely gone. It will never, ever return. Even if we emit zero CO2, which is pretty tough, the Earth will never cool. It'll stay as hot as we make it. However hot the Earth gets, that's it. But if we try very, very hard, we can avoid the worst outcomes. We can fight for each 1/10 of a degree to keep it from being worse than it otherwise would be. All we have to do is stop emitting CO2. So in the talk tomorrow, this is the point I'll be pausing for questions. I don't know what people will ask, but we'll see. So let's go on now to part two, the energy transformation. How do we stop emitting CO2? Well, we emit CO2 in almost everything we do, and I can't address all of these issues. What I want to address is just this bit. How do we stop emitting CO2 from our homes? So when we're living our normal lives in our homes doing nothing very special, we emit more than 30% of the UK's CO2 emissions, mainly from heating our homes, but also all the things we use in our homes. And it may be you live in a house like this, or a flat, or something modern, or a semi-detached house or something, but all our homes are busy emitting lots of CO2. And that comes from the energy that we use. So this is how we get energy in our homes. And it's the energy which makes life comfortable. It provides lighting and heating and all the access to all the gadgets we use. So what we do in the UK, at least, is we drill down into the North Sea, and there are the decaying remains of plants that lived millions of years ago. And because they're decayed in an anaerobic atmosphere, they produce methane rather than CO2. And the gas bubbles out, and we collect it and send it to power stations, where we go from chemical energy to thermal energy. We burn it with this reaction. CH4 plus 2CO2 goes to CO2 plus 2H2O. And we then take that thermal energy and turn a turbine that makes mechanical energy, and then the turbine rotates a dynamo and we make electrical energy. And to get 1 kilowatt hour of electrical energy, we need 0.45, we produce 0.45 kilograms of CO2 at the power station. So you're probably not aware of this when you use electricity. But that's not the only way we make electricity. Now we have nuclear energy, wind and solar, and they make electricity directly. And when they produce electricity, they don't emit any CO2 at the time. So to produce 1 unit of electricity, 1 kilowatt hour of electricity, their CO2 emissions are much, much lower than electricity derived from coal power station, from gas-fired power stations. So what we produce, what we consume, is a mix of these two sources of electricity, and it varies depending on how much the sun is shining, how much the wind is blowing, and so on. But on average, in 2022, every unit of electricity caused 0.23 kilograms of CO2 emissions, typically at the power stations. But we also send gas straight to our homes, and there we go. We burn it, so we do this reaction with oxygen in the atmosphere and get the thermal energy out directly. And by chance, that also produces 0.23 kilograms of CO2. So at the minute, in 2022, each kilowatt hour of gas or electricity produces about 0.23 kilograms of CO2 emissions. Now, in our homes, we typically use a bit under 10 units a day. And so our typical dwelling is emitting about 0.7 of a tonne of CO2, 0.7 of a tonne every year. Now, the reason you're not aware of that is that takes place at the power station. But when you're heating with gas, as most people are, you typically use 12,000 kilowatt hours of thermal energy, and that releases 2.7 tons of CO2, and all that is emitted straight out the flue off your family home. 2.7 tons. It's more than all the rubbish that you take out in a year. It's an absolutely phenomenal 2.7 tons. Is breathtaking. And so together, a typical family emits 3.4 tons, something like that, of CO2. And so how do we hope to stop this? Well, we have a plan. Well, that let me go back there. We have, first of all, is to make loads of renewable generation. Then we need to stop burning stuff and electrify everything. So let me show you what that looks like. We make more renewable and nuclear electricity. And then we don't need so much gas. And then we make even more renewable electricity, and then we need even less gas. And in that way, we drive down the main source of carbon dioxide emissions. And that's been going on for a while. Here's the carbon intensity of electricity in the UK. That means how many kilograms of CO2 are emitted per kilowatt hour. And this is 1998, and this is 2022. And so you can see back in the day, we emitted 0.46 kilograms of CO2 per kilowatt hour. Now it's down to 0.23. So it's come down by half. That's fantastic achievement. And we're hoping to drive it down to 0.1 by 2030. So stuff is going on to make electricity cleaner. Now, I want to talk to you very briefly about 3 things that are going to become absolutely commonplace in your home, and they are all part of this energy transformation. The first one is heat pumps. So heat pumps are astonishing. So the way we normally heat our homes is by using energy conversion. We put in electrical energy and we convert that to heat with 100% efficiency. Or gas, we can put in chemical energy into a boiler and get out heat. We only get about 90%. We throw away about 10% typically. In older boilers, we can throw away a quarter of the energy. But these are energy conversions. But a heat pump works in a different way. A heat pump moves heat. So if you have a fridge in your home, you already have a heat pump there. And a fridge is just an insulated box and with a heat pump. There we go. And what we do is we supply electrical energy to the heat pump, and it doesn't specifically make heat. What it does is it moves heat. It moves heat from inside to outside, And as it extracts heat from inside the insulated box, the temperature goes down. In the freezer, it goes down to minus 20 Celsius. And then outside, the temperature goes up. The outside of the fridge gets hot. And so in order to use heat pumps to heat our homes, all we do is change where we put the insulated box. We put the insulated box here and we take it away here. And now as the heat pump runs, it's moving heat from outside to inside, and the outside gets a bit colder, but we don't care. And the inside gets a bit hotter. And in fact, we don't need to go from minus 20 to 30. We can just very easily just go up to 20 Celsius is fine for heating homes. And 0 Celsius is pretty much the coldest it gets in most places in the UK. So that's what a heat pump does. It's moving heat. And the astonishing thing about it is for every unit of electricity we apply to the pump, we're able to move typically 2 kilowatt hours of heat, 2 units of heat. So those things all add together and we produce 3 kilowatt hours of heat. So this is 300% efficient for use of the electrical energy. If we just applied this to an electrical heater, it'd be 100% efficient. But this way we get 3 times more heat out. In fact, the heat pump that I have in my house, we get over a whole year, it's about 3.6 times. So what's astonishing about that, what's essential about that, this 300% efficiency is absolutely essential for this energy transformation. So we want to get our energy from renewable sources. So if we heat our homes with heat pumps, we need one amount of nuclear power stations, renewable wind farms and solar farms. But if we wanted to just heat our homes with normal electrical heaters, we'd have to have 3 times as much renewable energy, 3 times as many power stations. If you wanted to heat our homes with hydrogen, we'd have to have 6 times as many nuclear power stations, 6 times as much renewable energy. So the key to doing this quickly, the key to transforming the way we heat our homes quickly, is to use heat pumps. So let's just see what they look like. This is the one outside my house. It's got 3 connections. We just put in electricity and cold water, and out comes hot water for the taps and for running a central heating system. And inside, a heat pump just consists of a pipe filled with a working fluid. The working fluid is a substance like butane or propane, and that's a substance that's normally a gas at room atmospheric temperature and pressure, but if you compress it, it turns to a liquid. And as it goes round this pipe, it's changing all the time between being mainly gas and a little bit of liquid, or mainly liquid and a little bit of gas. And so the heat pump has a pump in which compresses the working fluid. And it also has a flow restriction here. So because of the flow restriction, when you compress it, this bit tends to get hot and at high pressure. So think about the way when you pump a bicycle tire up, it gets hot. And then this bit, when you expand it, it gets cold. So if you think about the way a spray can get cold when you spray things out of it. And so let's just colour the pipes to remember that. And so as we go round here, in order to make it operate, we make this cold end very, very long, and we blow air over it. Now, in this region, when we make it cold, we mean very cold. Typically, the working fluid is at minus 20 degrees Celsius. So if we blow air over this pipe at this, and say the air is at 0 degrees Celsius, that's still 20 degrees warmer than the temperature of the working fluid. So as the air is blown over the pipe, heat flows from the air into the working fluid. The working fluid then comes around and it comes to the pump, and when it's squeezed, it gets hot. And when it gets hot, we run it past the pipe where the cold water comes in, and these two, we transfer heat between these two, and out comes hot water. So in here, the working fluid might be at 50 degrees Celsius and the water might be at 40, so heat flows from the working fluid to the water. So overall, we've taken heat out of the air, put it into the working fluid, brought it round, and then taken it from the working fluid into the water. So that's how we've transferred the energy. The working fluid just goes round and round inside, it never leaves. And the astonishing thing is using this, we can reduce CO2 emissions immediately by 75% by using electricity and a heat pump rather than using a gas to heat our homes. And if you remember this slide back here, by the time we reach 2030, that'll be 90% reductions because electricity is getting cleaner. So that's a key part of how we're going to stop emitting CO2. And we can use solar photovoltaic panels. We have big solar farms, but you can also just put them on your roof. And how do they work? Well, we engineer the silicon to have a particular layer here. It comes in between a p-n junction. This layer is called the depletion layer. And when sunshine shines on the silicon, it creates a little electric current here. So we put a wire on the top and a wire on the bottom, and we can collect this electric current. It generates about 0.6 volts. So this is called a silicon cell. And typically what we do is we put lots of these cells together and we connect them top to bottom to stack them up in this way. Now, this is a photograph of one of the cells on my roof, and this is one cell. And so it's got 0.6 volts on the top relative to the bottom bit that you can't see. The key problem is that ideally, in order to collect the electrons that are created, you'd cover the top in an aluminium contact, but then no sunlight would get through. So you've got to have a pattern here that allows the sunlight to get into the body of the silicon where the current is created. If you look, you can see here are the very fine lines here, and the contacts are flowing. Here's on the top of this, and it's going underneath to the next one. So flow, and so there they go. That's one contact. That's another contact. And so when we look at a panel made up of lots of cells, they're adding up, and typically they add up to about 36 volts, and the current is about 10 amps. So it's a big current flowing through every one of those cells. So that's producing about 300 or 400 watts. Now the key thing about solar is this: it looks very fancy, the technology is amazing, but solar PV electricity is the cheapest electricity in all of history. It's the best way we've ever figured of making electricity. And the costs have come down dramatically in the last 10 years, down by 89%. And these are the other ways you can make electricity, and they really haven't changed very much. So solar and wind have plummeted in energy. Now, the interesting thing is that this plummet is not caused by any new technology or any new inventions. It's just the slow application of people getting better at making something. It's engineering, manufacturing engineering. Typically, you do something once, you achieve it, that's great. Doing it the second time, you do it better. Doing it the millionth time, you get really, really good. And then the last thing I want to talk to you about is batteries, which may not seem like they're part of the solution, but they absolutely are. This is a graph showing through the month of October 2022, all the generation in the UK. This is the amount of electricity in gigawatts, 10, 20, 30, 40. See, the peaks are almost 40 gigawatts. And here's the green is nuclear. The pink ones are onshore and offshore wind. You see yellow is solar. Astonishing, we're still generating solar electricity in October. But the blue one is gas. That's the one where all the CO2 emissions are associated with. And these peaks are the dirtiest generation of all. They're really, it's where, but supplying those peaks is essential to keeping the lights on. If people demand electricity at that time and there's no power, then there'll be blackouts. Stuff will break. So this is this key place we'd like to reduce emissions. So let's see how batteries help. Well, this is the one in my house. It stores 13.5 kilowatt hours of electricity. It's about 4,500 AA batteries in magnitude. And it has a computer looking after it. And it's looking to see how much solar energy is coming on the roof, what the demand in the house is, what the grid's doing. And so this is what electricity consumption looks like in my house. This was on the 7th of October 2022. And so this one is the household demand. This is what we use. This is the energy we take from the grid. This is solar energy, and this is the battery. Let me show you. So this is a typical day for a household. We've got some base amount of electricity that we're using to run the heating, and it's about 200 watts or something like that. Overall in the day we used 11.7 kilowatt hours. But look at this massive peak at tea time, more than 5 kilowatts that we used at dinner time. That's why we get that big peak on the graph I showed you previously. But we didn't take any of that from the grid. We bought all our electricity in the small hours of the morning. So this is midnight to midnight. So we charged up a battery, 6.8 kilowatt hours from the grid during the night. And then during the day, we're running off the battery, so we take nothing from the grid. And then in fact, we charged up the battery again, and the battery got full, and we gave a little bit back to the grid. And that big peak, we only needed an extra little bit of electricity to supply that peak. So here's the solar. So again, this is midnight to midnight. You can see that it was a cloudy day, but there were sunny spells. And so we got some generation, 6.5 kilowatt hours of generation. And here's what the battery was doing. We charged it up overnight, and so it's stable. And then we ran from the battery during the day. Then the battery got recharged and full again. And then we ran it down overnight. So what this allows is, in this diagram here, instead of having to generate for everyone at the same time, we can shift this generation into a time where we don't need the dirtiest plants, so we can use the existing fossil fuel plants more efficiently. And again, the cost of batteries, just like again, not based on new technology, but just like solar, is plummeting. It's absolutely, and it's still getting cheaper. So using a heat pump, solar PV and a battery, it's possible to dramatically reduce CO2 emissions from homes. So with these things in my home, it's come down by about 80%, and in 2030 it should have come down by 90%. So these three things are part of the energy transformation. Practical things that they require no new inventions. They are available now. You can buy every one of them off the shelf. So here's the question: is it possible to live a carbon zero life? No, not yet. But it is possible to reduce emissions from our homes by 80 to 90% right now using, we don't need any magic, we don't need any new physics, we just need to devote ourselves to saying this is the important thing we want to achieve as a community. And the thing I want to tell you is that carbon emissions and climate change is such a depressing subject, absolutely depressing. But I want to tell you that this energy transformation will provide thousands, millions of opportunities for you, whether you want to be an installer of heat pumps or solar PV, whether you want to be an entrepreneur, whether you want to be a production engineer, whether you're an accountant, or whatever kind of engineering you're going to do, coping with climate change is going to provide massive opportunities for you, that there is a great world for you, and there's nothing more noble than fighting this fight. And also, we need you to figure out how to stop the last 10% of emissions. Okay, can I say thank you very much? You can get in touch with me. This is Twitter. This is my email address. Can I wish you good luck? God bless.